Okay, so let's continue our lecture on LASSO. In the last lecture, we have to talk about methods to solve the LASSO regression, which is pathwise coordinate descent. The second method that we use is called projected gradient descent. So this is also a very popular method. So this method is based on the following thing that we split our parameter into two parts, which is W plus minus W minus. So the definition of this W plus is the maximum of W and 0, W minus, the definition of is minus minimum. W and 0. So that means both of that will be bigger or equal than 0. So if we take this, then we can show this W is actually equal to W plus minus W minus. So this is, one of that is either 0 here, right? So then my like one norm of my W is actually can be written as summation of D from, and let's just say I here, okay? I from 1 to D, then Wi plus Wi minus. All right, so this is kind of you basically actually split up the positive part and negative part. Then so I want to remind you our an objective function, and our objective is to minimize the W of xw here minus y plus lambda of the one norm. So this is equivalent we do for the minimization of W plus is bigger or equal than 0, W minus is bigger or equal than 0. That we apply this thing that is W plus minus W minus, subtract Y plus lambda of I from D, Wi plus Wi minus. Okay, so this is how you actually do that. And obviously this is not very, there's no differences right now. And we just turn this unconstrained optimization into constrained optimizations. So what we do is we can solve everything by something called projected gradient descent. So what is the projected gradient descent is I actually going to split the W into and W plus and W minus. This basic says I'm going to turn this into two portion W plus and W minus right here. Instead of one single W here. And also we know right here, so this whole thing, and we can just simply take partial derivative with respect to W plus and then W minus and respectively. So what we do is we can turn this into the following: W t plus 1 plus W t plus 1 minus. So this is just the gradient descent. We take the P plus, this is projection here, of W t plus W t minus plus of minus eta t gradient NLL. Oh, we have talked about this gradient of, let's say, W plus of everything right here plus plus eta t of gradient W minus of this whole thing right here, and subtract the eta t lambda times like bunch of ones here, ones. So this is basically, we create this projected gradient descent to work on this and like step by step. So this P plus is the projection onto the region that W plus is bigger than and bigger equal than 0, and W minus is bigger and equal than 0. So P plus wait. Let's say X and Y. It is equal to the maximum value of X and 0 and the maximum value of Y and 0. Okay, so basically, if X or Y here component is less than 0, it will move into 0. If it is positive, just stay as positive and a positive. That means I basically project W plus and W minus into the domain of W plus is bigger or equal than 0, and a W minus is bigger or equal than 0. Okay, so this is something that is quite important. So I mean, then and the rest, it just becomes a gradient, like projected gradient descent. Another thing that is also very important is this LASSO is actually a biased estimator. Sometimes if you want an unbiased estimator, so something called debiasing. So what you can do is you can and performing everything in like with a two-stage estimation process. So you can and debias. So the debias has a two-step. First is estimate the support of the weight vectors. So basically, just identify those features are not zeros. So we're just using LASSO to identify those features using LASSOs. So this is basically just feature selections. And then we will re-estimate the coefficient using the new selected features by using the least squares. So, and what we do is we re-estimate the coefficients using least squares of selected features. So basically, we're just using lasso to select features, then we just take those important features, then apply the least square. This ensure this is actually has a and the estimator that you got is unbiased. So this is something called debiasing. This is not absolutely necessary, but sometimes if you want to have like unbiased estimators, then that's the process you can do. And also another thing is to choose lambda. And of course, we have a talk about this. Even in the ridge regression, it's basically you can use either holdout or cross validations. I mean, either just simple cross validations or k-fold cross validations. Either ways will be fine. And also, what is the range of lambda you should be choosing here? So this is the question, right? And you cannot choose like range and the lambda forever, like and to arbitrary large. So this is something that we will be very interested in. So the range of lambda to choose from. So the first thing, as you can see right here, I mean, smallest possible lambda is 0, right? So if lambda is 0, then W hat is equal to the least square solutions. And of course, we know if this lambda is large enough, then like everything just like becomes 0. So there will be some critical lambda, then everything just be muted into 0. So this is the situation that the gradient of this, I mean, the first component, which is negative log likelihood, actually cancels out the gradient of the penalties. So that means my penalty is so strong that even I'll take like every component of the gradient of negative log likelihood. So that means, so all we need to do is that will be the situation that the maximum will becomes the gradient of Wj of my RSS evaluate 0 absolute values, then maximum J. So what is that? So this is basically maximum of J of xj transpose, 2xj transpose of, I believe is right here, x times w minus y. But we know we are evaluated at 0, so this is basically maximum of J of 2xy transpose of y. So like xj transpose of y, an absolute value here. So this is nothing but we take 2 times of the maximum value of x transpose of y with the infinite norm. So then the range of x and the lambda will just becomes between 0 and the lambda max. Okay, so that means if my lambda is even bigger than lambda max, that means this and if we take the gradient and each component of the gradient coming from penalty is bigger than the largest part coming from the an RSS. So as a result, it will always give you negative values for any kind of y. So as a result, it will goes just goes to zeros. All right. So that just tells you if you want to choose your lambda, that would be the range from 0 to like in the lambda max. That would be the range that you should be working on that. Okay. So let's talk about coding. Let's implement that from scratch. Okay, run it all. So before you actually implement everything, here is another tips in coding. So first thing is, in a lot of cases, for loop can be very slow, as we already mentioned. If you can vectorize, try to vectorize it. And also the pseudocode that we provide right here, it's not fully optimized. This is just a way, but that doesn't mean it's the most optimized way. In fact, in the homework, you actually are going to work through and trying to figure out, is there any way that you can speed up the computations? And there are a lot of ways that you can pre-computing certain quantities before the loop, and you don't need to recompute. Exact the same thing again. Sometimes there will be some small changes, but these small changes could still speed up things significantly because we have a large for loop going on. If for each loop you and your method speed up by 0.01 seconds, but say if we are and running for more than 10,000 iterations, this still could be quite significant. And also, you can check whether your objective value is non-decreasing with each step or not. This is obviously very important. You need to be sure that your an objective value is non-increasing. And of course, common problem is you need to decide on suitable stopping conditions. A common criteria is to stop is no element of W changes by more than some small tolerances during iterations, then you should stop right here. If you want your algorithm to run faster, you can lose this condition a little bit. And in a lot of cases, you need to solve this LASSO problem on the same data set for many different value of lambda during the cross validations. This is something called a regularization path. That's something I ask you to do in the homework. There are multiple ways to make things much more efficient. One way to do this efficiently is you start with a large lambda. Then for each consecutive solutions, initialize the algorithm from previous solutions. This is based on the assumption that if lambda is close enough, the solution will also be close enough. Okay, so this is some assumptions. It's quite common. It's making sense. And you can decrease your lambda by some constant like ratio, for example, by a factor of 1.2 until finish. So this is a very good way to do so. One of the reason, the reason that we don't do that like with the with the linear spacing is because usually these like penalty like parameters actually is searched with the logarithms and the parameters. So that's why it will be more logical to decrease this lambda by a constant ratios rather than you are going to linearly and spacing this lambda out. This is an option, but that doesn't mean you shouldn't do that with the linear spacing of the lambda span. And you can still do that. All right, so this is the main functions that you are going to work with. So this is, still we have a list. Like lasso solve, we have, and QR solve. This is my lasso function right here. This is by no means optimal. There are multiple ways to try, and you can optimize it. If needed, here we're just doing in the round robin fashion. You can try it with other like randomly. So that will be for the homework. Okay, so here is the strategy right here. So first things that we pre-compute this AJ right here. So this is what we are doing because AJ is not changed at all. CJ is changing all the time, so that we are going to compute this. But this CJ right here is not optimal. So in the homework, I want you to think about the way to actually and find a way to and optimize this part. And you can using this time and percentage, put the time to check how fast and how slow and how efficient of your programming right here. So hypothetically, if you can optimize that, you should see some speed up for this specific data set. Okay, so you calculate the CJ, you calculate CJ over AJ. Then this update is nothing but soft thresholding right here, which will be something like this sign of CJ over AJ, maximum CJ over AJ, absolute value minus lambda over AJs and the zeros. Right, so this is much more efficient than this and the three cases discussions. I don't want to write any if condition. If condition will be really, really slow in Python here. So that's why I write out everything like this. So this is just one line of code. You can just assign this everything quickly. If W update is less than some like setup tolerance like value, and each component of my W update is less than some like tolerance, I believe this tolerance that I said is 10 to the minus 6, then I will stop. So this is what, and when I will stop right here and return my W here. Right, so this is very straightforward. It only take about, I think, 20 lines of programming, which and fairly straightforward. So we use the same data set, and we have done this before, but this time we just try the 6th orders polynomial to see whether and we are using this lasso to pick and choose the feature selections to see whether they can find right amount features in these cases. Because we're not trying to using all 7 features from x to the 0 to x to the 6. That would be way too expensive. And that will very likely create overfitting issues. As I said, we did it and the last time we need to do some feature scaling. The reason just because my x right here scales so dramatically because we are taking this power of 6. This is a really, really big range. And think about the maximum value that we got is about 20 for the x, like 20 power of sec, and the 6, this is really large values, right? So it will be much more convenient to rescale the data with the minimum and the maximums to ensure everything just within the domain of 0 to 1. Okay, so you take the minimax scalar, then here, right here, I'm saying you could, and this is basically the like maximum like lambda you can do right here. There are multiple ways that you can do, and the linear span, and you can do the linear span as I mentioned right here. So from 1 to like this large values, I'm going to linearly truncate into 100 points. All what you can do is you can and divide it by 1.2 at each iterations, right? So either one is fine. I'm not saying and which one will be the better one. You actually need to test that to see which one is the better one. And we're going to store all the W values that are needed. So you can see this lambda span is actually the and the linear span. So that will be from 1 to 54 right here. So what we do is we just try a like simple test right here. This is not efficient right here because my initial condition here is always assumed to be 0, right? This is not strictly follow the tips right here that if we using and need to solve this lasso on the same data set for different value of lambda, what you can do is you can initialize this algorithm with a previous lambda. Here, I don't even have this option to imply and to apply this like lambda and to on this initializations. What you can do in the homework is you can modify this code of these functions that you can include the initialization of the lambda. As the result, once you creating such kind of like regularization path, actually this can make this program or code much more efficient. Okay, I didn't do that, but you should do that in the homework. This is your opportunity to make your code more efficient. Okay, I install this solution right here. Then we can plot all these parameter weight. You can see, so initially when lambda is 0, almost every component just being non-zero. Then like gradually, and each component is being muted to 0. And you can see sometimes it was previously 0, then it will like increase, then decrease again. That is totally possible. In Lasso, that doesn't mean, I mean, the solution is always monotonically decreasing. We don't guarantee that for sure. But in general, the trend is when we have a larger and a larger regularization, and the coefficient 10 will like going to 0 gradually, and the sum of the value will completely muted to 0. But it is totally possible some feature was previously muted to 0, then suddenly turn on into some like positive values. That is totally possible. Okay, we never actually like and eliminate that kind of situations. So this is some like an regularization process for the lasso here. And also we can actually count how many non-zeros that we have for each of the W here. You can see, so I'm here just plot the number of non-zeros. So initially we have only about like 3 of this. We increase into 4, then 3, back to 2, back to 1, back to 2, back to 1, and like back and forth. right? So you have seen some like and we have like and so I mean this indicated we have two features with this indicated we have like one feature. This indicated we have three features and so on. And then what we can do is we can extract, see, the point of everything is see we can find out and the right amount of features to work with, right? So, and initially we have 7 features, and the point of Lasso is to do feature selections. So what we can do is we can do the subset selections. We can extract these unique non-zero and features by doing so. So, and we can find out all these like non-zero entries, and we find out these like unique tuples. So these are the unique tuples of combinations. For example, right here, if that tells me my 0, 1, 3, 2, 0, 1, 3, 4, these 4 features are considered to be important. That corresponding to x to the 0, x to the 1, x to the third, x to the 4th, and so on. Right? So this is basically and these will be an important features. Of course, we are having more testing data, and we're going to work with cross validations to perform and to try every set of the features to see which one and which and subset features perform the best. So then what we do is we go through all and these are all the candidacies of the features, right? So and compared to 2 to the D is 7 right here. This is significantly smaller. We only have 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 different features to choose from. 9 sets of features to choose from, and rather than 2 to the 7. So that's the power of the Lasso. Actually give you a very convenient way to choose the features from. And we tested out, and to do this just a simple linear regression. Here we are trying to find out unbiased estimator directly for this problem. And this is the error for the RSS right here. You can see the smallest one is chosen from this one right here, which is the 5th of this. This corresponding to 0, 1, 3. So that means from the Lasso, it tells me the best feature that we got is W0 plus W1 times X plus W3 times X cubed. You can see this is different from the ground truth, right? So the ground truth is we only have a first order and a second order. But from Lasso, we have a 0th order, first order, and a 3rd order, right? So this is different. But if we, although this is different, we didn't fully recover the ground truth. But if we're using these 3 features and make a plot, you can see this actually did pretty good job. And you can see the curve fits to this and like testing data set very, very well from 0 to 20s. So that's why, although this Lasso doesn't fully recover the ground truth of features, but they also, and find out the features that is close enough and good enough to work on, which is looking like something like that. And of course, you can argue there's some deviation on both ends, but in the middle, it looks pretty reasonably good. All right, so this is Lasso. But you can also combine the Lasso regression with the ridge regressions. So if we combine both of that, this is something called like elastic net. Basically, ridge and the Lasso combined. So when will we and when shall we using this kind of and approach is if we have a group of highly correlated features. For example, we have a talk about the number of bathroom and the number of the showers. When we do this house predictions, house price predictions. If we do, so if we have highly correlated features, there are multiple ways to deal with that. But if we just apply the lasso, it will tend to select and amongst and the dumb arbitraries. So basically, lasso may assign the weight on both features very arbitrarily. So this is a big issue if we have a highly correlated features when we do regressions. It will be better if we can select them all together and group them together. And also, if we trying to add some ridge regression, it tends to have a better predictive performances in that cases. So we also want to add a little bit ridge to ensure we have a better performances. So what we can do is, instead of we find those highly correlated features, I want my algorithm can automatically identify these highly correlated features and being treated as implicit group by themselves. So I don't need to do it by themselves. So what you can do is you can use this kind of elastic net. This elastic net is a hybrid with of the lasso and the ridge. Actually can work out this kind of highly correlated and features very well. So this is basically the objections that we have. It's almost the same, but the penalty that we're going to adding is lambda1 of the one norm and the lambda2 of the two norm. So this is, instead of you adding one penalty, you're adding two penalties. So if we add two penalties, because of this L2 and the regularization penalties, this function turns out to be strictly convex instead of convex. So in these cases, there are always a unique global minimum, even if X is not full rank. So this is, basically similar argument coming from the ridge regressions. And also, any strictly convex penalty on W will have some grouping effect. That means if those and regression coefficient with highly correlated features will tend to be equal. So that's why this can give you some a good idea, and it can handle those highly correlated features automatically. One thing that I can think about is very extreme cases that if J and the kth column are completely identical, and you can show that their estimate will actually be equal, like Wj will equal to Wk on elastic net. But in lasso, you will see it's possible that Wj is equal to 0, but your Wk is not equal to 0. So this will not be stable at all. So this just gives you some idea. Just coming from this elastic net, it can help to identify these highly correlated features and handle these highly correlated features automatically. For this, we are not going to implement that. It's just like give you some idea. If you have that kind of situation, you can implement this kind of elastic net situation and regressions. This is a quick summary for this regression part. Least square, basically it's like, and likelihood is basically a Gaussian distributions. And the prior, we don't actually have a prior for the least square. If you think about, we actually have the, like prior, it's basically a uniform and the distributions. And for the robust and regression here, we didn't get into too much detail, but just I want to and emphasize for the norm of RSS right here, in the least square we are using two norm. In the robust regression we are using one norm. So basically that corresponding to the likelihood of the robust regression is actually considered as a Laplace distributions instead of Gaussian distributions. For the ridge regression, the likelihood for the ridge regression will be Gaussian because we are using the 2 and square root 2 norm of the RSS, and the prior and distribution of the parameter is considered to be zero mean Gaussian distributions. The differences between LASSO and the ridge is if we assume prior distribution to be a Gaussian, that corresponding to Tikhonov and a regularization, that would be the L2 regularizations. If my prior distribution of the parameter is the Laplace distributions, that corresponding to L1 distributions. Sorry, that will corresponding to L1 regularizations. And this is something called LASSO here. Okay, so this is basically a quick summary on the regularization as well. If you work with the regularizations, there are like multiple and regularizations that we can impose even with the layer of the problems, and even with the neural network, even with and other classification problems, you can also and apply those regularizations. These regularization things is very universal. When you build the models, you can always adding certain regularizations to prevent overfittings, right? So, and the reason that we add regularization is because we don't want to have this overfitting issues. Here are two regularizations we are keep talking about. One is L1 regularizations, another one is L2 regularizations. Different regularization will give you different effect. For example, if for the L1 regularization, it will introduce more sparsities to the models. It will be less sensitive to outliers. If you have outliers, L1 and regularization, it will be less sensitive. L1 regularization, because it introduced sparsity, it will be helpful for feature selections, make the model more interpretable. L1 regularization is more computational efficient as the whole model because of the sparse solution. It will have, and you can compute things much faster. You don't need to do inner product for the whole W features. And if you have a really large feature spaces to work with, it will be much more computational efficient if we apply this L1 regularizations. L2 regularizations will make those weight small, but not precisely equal to zero. L2 regularizations will be sensitive to outliers because we have the square terms that we have. But the benefit of L2 regularizations usually works well in practice, right? In practical data set, this Gaussian prior is very reasonable assumptions. So that's why L2 regularization can work very well in practice. Even with the least square, sometimes we just adding a little bit and enrich and regressions. It generalized tends to stabilize the whole problems and make everything and work very well. Okay, so this is basically summary for the LASSOs. The data pre-processing part, it will be covered in the next part. All right, so that's all for this part now.